In this video, we're going to introduce our paper modeling the distributional uncertainty for Salient object detection models. First of all, what is distributional uncertainty? The deep hybrid model proposes that the posterior joint distribution of a testing sample can be written as a product of data uncertainty, distributional uncertainty, and model uncertainty. The data uncertainty is inherent in the dataset generation process. The model uncertainty represents the uncertainty of model parameters given the current training dataset. And finally, the distributional uncertainty explains the distribution gap between the test sample and the training dataset. It occurs when the test sample fails to fit in the model based on the training dataset. Recently, most of the existing salient object detection, or SOD models, focus on improving the overall model performance without explicitly explaining the discrepancy between the training and testing distributions. We compute the VOG scores of samples from the DUTS testing dataset, where the difficult samples are distinct from the training set. In this paper, we define OOD samples for saliency detection as those break the basic saliency priors. In this case, saliency OOD is continuous instead of discrete. In this paper, we aim to explore the distributional uncertainty estimation for salient detection. Specifically, we'll investigate the existing class-aware distributional gap exploration techniques and adapt them to model the distributional uncertainty for a class-agnostic task. We perform extensive experiments to explain both the advantages and limitations of each technique and draw some conclusions. Next, we will detail each of the methods we use. Firstly, the classic methods. Dropout randomly prevents the activation of some neurons during forward propagation. Therefore, the distributional uncertainty can be obtained by multiple forward passes. The deep ensemble method sets multiple decoders for the shared encoder and obtains a distributional uncertainty map from the multi-head predictions. Long-tail learning-based methods are designed to address the problem of class imbalance in the training data by suppressing the head data and promoting the tail data. Following the conventional long-tail learning techniques, we introduce continuous version long-tail learning for saliency detection. The model rebalance technique designs a diverse expert learning network to model different distributions. The loss reweighting method and post-hoc method using the distribution number of classes in the training dataset to weight the loss or lodge it and achieve the data balance. The distributional uncertainty map is finally calculated as the entropy of prediction. The next one is the commonly used single model uncertainty estimation method, which separates in-distribution and out-distribution data by computing a reliable OOD score. The single model uncertainty modeling methods can be achieved via post-hoc techniques and training techniques. The post-hoc techniques compute confidence directly from model output probability or energy score formulation and standardize lodged space. There are also solutions that obtain the uncertainty map using gradients. OOD scores can also be learned through network training. The loss function regularization method uses an additional head to learn the true class probability, which directly reflects the confidence of predictions. The data reprocessing method adopts prediction variation as method uncertainty by training on a dataset shifted by random image biases. In addition, the weight regularization performs rectified activation on the features of the model through a set threshold, and then feeds it to the later layer to get the prediction, which can sufficiently preserve the activations for in-distribution data and truncates high activation to limit the effect of noise. The last method is the test time strategy. The test time training strategy adopts the testing sample to the trained model by optimizing its specific part of the parameters. The loss function mostly defines the consistency of the prediction results of the data before and after the augmentation. In our experiments, this is the consistency of the teacher-student network. Test time augmentation aims to improve network performance through data augmentation at test time without adding additional network parameters for training. In our experiments, a loss prediction network is used to select reliable augmentations, and the multiple transformations are superimposed by cycling. The final prediction is a weighted sum of the results of multiple cycles. Next is the experiment part. At first, we display the basic setups. Here we show the results of the conventional methods, dropout and deep ensemble. Compared with base model and dropout strategy, the deep ensemble method integrates the information of multiple decoders, making it more accurate in distributional uncertainty modeling. Here are the results of long-tail learning-based methods. We observe consistent inferior performance of each solution compared with the base model. The main reason is that long-tail learning models usually rely on the number of each category as class balance weights, where the basic assumption is that there exists no transition across categories. However, as saliency is a continuous attribute, foreground and background can be transferred flexibly. We believe the continuous adaptation of discrete long-tail methods is less effective for our task. Here are the results of single-model uncertainty techniques. We find the post-hoc techniques fail to improve the uncertainty quality. On the contrary, the training techniques, especially TCP and React, are effective in generating reliable uncertainty map. The visualization results also clearly shows the advantage for both accurate prediction and reliable uncertainty generation. Finally, here are the experimental results of test time solutions. We observe that the test time training method may lead to a model that focuses on the misclassified pixels in self-supervised learning, resulting in performance degradation. In this case, carefully designed strategy to prevent model from drifting too much should be imposed. On the other hand, the test time augmentation method has a potential to generate reliable uncertainty if proper augmentation policies are learned. To sum up, in this paper, we make the first effort in investigating the out-of-distribution discovery issue for salient object detection. To explain the distribution gap and draw some conclusions. Firstly, we verify the effectiveness of deep ensemble and the single-model uncertainty estimation technique in generating reliable distributional uncertainty. Secondly, we find the long-tail learning solutions fail to generalize well to our class-agnostic task. Finally, we also point out that the test time training strategy is promising to further explore regularization terms to control the drift degree of model for better uncertainty generation. This is the end of the video. For any questions, feel free to contact us. Thanks for watching.